Hello everyone, welcome back to my YouTube channel. In this video, I want to continue to solve the last 4 questions, which is question number 16 until question number 19 from EJU Physics 2019 first session. You can check link on the description box below if you want to watch the solution for the other problem on this paper, or check my EJU playlist for another paper. Okay, in this question we have a battery with EMF 1 volt. So I have a battery with EMF 1 volt, a switch, as you can see here, this is the switch, the resistor of resistance 1 kilo ohm or 1000 ohm, and then two capacitors C1 and C2, each of with capacitance of 1 microfarad. So these two capacitors, each of them have capacitance 1 microfarad, are connected as shown in the figure below. Initially S is open and C1 and C2 are not charged, and then S is closed and C1 and C2 become charged. The internal resistance of the battery is negligible. The question is, what is the quantity of joule heat evolved at R? R is the resistor when S is closed until C1 and C2 become fully charged. So basically in this question we want to find the heat energy or the energy in this resistor. We want to find energy dissipated from this resistor. First thing first, because I have two capacitors here and then these two capacitors are connected in series, we can combine these two capacitors into one capacitor. If we want to find the equivalent capacitance of two capacitors which is connected in series, we can use the equation 1 over C total or C equivalent is equals to 1 over C1 plus 1 over C2. This is the combined capacitance which is connected in series. Both C1 and C2 are 1 microfarad. So I got 1 over C total or C equivalent is equals to 1 over 1 plus 1 over 1. 1 plus 1 is 2. Then I get 1 over C equivalent is equals to 2. Therefore, C equivalent is equals to 1 over 2 microfarad. So if I combine these two capacitance into a single capacitor, I have a capacitor with a capacitance 1 over 2 microfarad. So now you can see these two capacitors as one capacitor with capacitance 1 over 2 microfarad. And then, since these two capacitors or our new one capacitor is connected in series with 1 volt of battery, then the total voltage or the total potential difference between these capacitors is equals to 1. So this is the total capacitance, and then I have the total PD which is equals to 1. I write it down as V equals to 1 volt. So I can find the charge. I have capacitance, I have V. If I want to find Q, we can use the formula C equals to Q over V. And then I will substitute C as 1 microfarad. I write it down as 1 over 2 micro. And then I want to find the Q, which is the charge, over V. My PD is 1. From here I got Q is equals to 1 over 2 microcoulomb. The unit of charge is coulomb. Since there is micro here, then my total charge is 1 over 2 microcoulomb. Since I already get the charge in this capacitor, I can find the total energy stored in this capacitor. Total energy stored in this capacitor, we can find the total energy by using equation energy stored in the capacitor is equals to half QV. My charge is 1 over 2 microcoulomb, and then my PD or voltage is 1 volt. Then I got the total energy stored in the capacitor. 1 over 2 times 1 over 2 micro times 1, I got 1 over 4 microjoule. You have to remember, yeah, the unit of energy is joule. Then energy stored in the capacitor is 1 over 4 microjoule. And then I can find the total energy provided by this battery. Electrical energy provided by the battery is V times I times T. This is the equation that we can use to find the total energy or total electrical energy stored in the battery. V is voltage, I is electric current, and then T is time. I times T is equals to Q. The definition of current or electrical current is rate of flow of charge. So I is equals to delta Q over delta T. That means I times T is equals to Q. So electrical energy is equals to V times Q. Our EMF or voltage is 1 volt. And then our Q is 1 over 2 microcoulomb. That means my energy from the battery is equals to 1 over 2 microjoule. 1 over 2 microjoule. That means if I want to find the energy in this resistor, I can find it by subtracting 1 over 4 with 1 over 2. You can see like this, yeah. This is the total energy. This is the total energy. Some of the energy is used or stored in the capacitor, and then the rest is dissipated as heat by this resistor. So by using the conservation of energy, energy in this capacitor, which is dissipated as heat, is equals to the total energy provided by the battery minus energy stored in the capacitor. That means heat energy dissipated by the resistor is 1 over 2 microjoule minus 1 over 4 microjoule, which is 1 over 4 microjoule. This is my final answer for question number 16. The answer is 1 over 4 microjoule, which is number 1. Okay, let's continue to question number 17. As shown in the figure below, 3 sufficiently long straight conducting wires are parallel to one another and are perpendicular to this page. They pass through vertices A, B, and D of square ABCD with length A within the plane of this page. So if you see from this diagram, this is a very long straight wire, this is very long straight wire, and this is very long straight wire. So we have 3 wires here. The wires are parallel with each other and perpendicular to this page. An electric current of magnitude I flows through each wire. So, on each wire there is an electric current with magnitude I. The current in the wire passing through A flows from the front of this page to the back. So we can say that current in wire A goes into the page, and then current in wires B and D flow from the back of this page to the front. So in B and D, the direction of current is out of the page. The question is, what is the magnitude of magnetic field produced at C? Produced at C by the currents flowing through the three wires. So we want to find the total or resultant magnetic field at C by these three wires. Also, which arrow among A until D in the figure indicates the direction of the magnetic field. So basically we want to find the magnitude and direction of the magnetic field at point C. The concept that we need to answer this question is, if I have a wire, you can imagine this as a wire, and then if there is a current in this wire, assume that the direction of current is going up, then around this wire there is a magnetic field. Around this wire there is a magnetic field. The direction of the magnetic field can be determined by using right hand grip rule. I think you need this concept. So if you haven't learned about this, I suggest you to go on Google to find out the concept behind right hand grip rule. Right hand grip rule. Basically, this is the way how we determine the direction of the magnetic field. And then if we want to find the magnitude of the magnetic field produced by this current carrying wire, we can use equation B is equals to mu null I over 2 pi A. Mu null I over 2 pi A. I is the current, mu null basically is a constant, and then 2 pi times A is the distance from the wire to the point in which we want to find the magnetic field. So basically, assume I want to find the magnetic field at this point. Then A is the distance from the wire to that point. This is A. So to answer this question, we need to know two things. The first one is right hand grip rule, and then the second one is this formula. Okay? If I apply these two concepts to this question, then we have three magnetic fields at point C. One is produced by A, and then one is produced by B, and then the last one is produced by D. If we want to find the magnetic field produced by A at point C, by using right hand grip rule, the direction of magnetic field produced by A to point C is directed to B. I do not explain how to use right hand grip rule, yeah. So if you still do not know the basic concept of right hand grip rule, you can find it on Google. Okay, magnetic field produced by A at point C is directed towards B. I will write it down as BA. This is magnetic field produced by A, and then magnetic field produced by B to or at point C is directed upward here. I will write it down as BB. B is magnetic field, and then this small b is produced by point B. And then the last one, magnetic field produced by D at point C is directed to the right like this. This is BD. BD. So by finding the resultant of these three fields, we can find the final answer of this question. Like this. BB and BD have the same magnitude because the current flow through B and through D is I, and then the distance from B to C and D to C are equal, which is A. So BB must equals to BD in magnitude. By using this equation, I can find BB, which is equals to BD, which is equals to mu 0 I over 2 pi A, the distance from B and D to point C is A. This is magnetic field produced by B and produced by D. And then magnetic field produced by A to point C is BA. BA is equals to mu 0 I. The current passes through A is also equals to I, but the distance from A to point C is the diagonal of this square. Since the side of the square is A, then the diagonal is A square root of 2. You can simply using Pythagoras theorem to find this. So mu 0 I over 2 pi A, the distance is square root of 2A. This is BA. And then if I try to find the resultant of these three magnetic fields, as you can see from this diagram or this diagram, BB and BD has the same magnitude, and then the direction of BB and BD is perpendicular with each other. So the resultant of BB and BD is diagonally like this. This is the resultant of BB and BD, diagonally like this. The angle is 45 degree because BB and BD are equal in magnitude and they are perpendicular each other. Then the resultant must be diagonally 45 degree. To find this resultant of BB and BD, we can simply using Pythagoras theorem. This is mu 0 I over 2 pi A, and then this is also mu 0 I over 2 pi A. Then the diagonal or the resultant is mu 0 I over 2 pi A square root of 2. You can assume like this, yeah. Assume that this is B, and then this is B, which is this one is B. Then the resultant is square root of 2 times B. Then the diagonal or the resultant of BB and BD is mu 0 I over 2 pi A times square root of 2. Mu 0 I over 2 pi A times square root of 2. The angle is 45 degree. 45 degree. Okay, and then to find the magnitude of the magnetic field produced at C, which is denoted as H, you can see from these two vectors. This one is going 45 degree diagonal up, and then BA is also 45 degree diagonal down. So these two are opposite vectors. If we have an opposite vectors, then to find the resultant, just subtract it out. As you can see, this is my BA, and then this is my B, as I assume this as B, yeah? Assume this as B. Then to find H, just subtract it up. That means H is equals to B minus BA. B minus BA. My B is this one. I will rewrite this into square root of 2 over 2 mu null I over 2 pi A minus this one. I will write it down as 1 over 2 square root of 2 mu null I over 2 pi A. Wait a minute. Wait a second. I think we do not need 2 here, yeah? I will erase it. Okay, we do not need 2 here. Let me check a moment. Square root of 2 over 2 and then 1 over 2. Okay, that's it. And then if you factorize mu null I over pi A to the front, then the rest are square root of 2 over 2 minus 1 over 2 square root of 2. And then by simplifying this expression, I think we can find the magnitude of the magnetic field and also the direction. Mu null I over 2 pi A. If I times square root of 2 on numerator and denominator here, so I got 2 square root of 2. From this one, I got 2 minus 1. Sorry, I keep writing 2 here. Wait a minute, let me delete it. Okay, like this. And then my final answer is mu null I over 2 square root of 2 pi A. If I rationalize the denominator by multiplying it with square root of 2 over square root of 2, then my final answer is mu null square root of 2i over 2 times square root of 2 times square root of 2 is 4. 4 pi A. Then the correct answer is, I do not know why in the choices below they do not write mu null. They only write down 3 square root of 2i and then square root of 2i and so on. I do not know why there is no mu null here. But if we try to ignore this mu null, then my final answer is this one, which is either number 5, 6, 7 or 8. 5, 6, 7 or 8. And then to find the direction, if you see from my calculation, when I calculate h, I write it down as B minus BA. And then I got, this is my final answer and this is positive. That means B is greater than BA. That means the final direction of this magnetic fields is going diagonal up. The same direction as B. Because when I write down B minus BA, we got the final answer is positive. That means B is greater than BA. So the direction is letter D. Then my final answer is number 8. Okay, this is question number 17. Let's proceed to question number 18. A charged particle, quantity of electricity Q and mass m, is projected with speed v perpendicularly into magnetic field of flux density B and begins undergoing uniform circular motion with radius r within the magnetic field. So basically you have a charged particle. I assume the charged particle is positive, and then you project this charged particle into a magnetic field. I assume the magnetic field is going into the page of paper. And then when this charged particle enters the magnetic field, it will undergoing uniform circular motion. The question is, which graph represent the relationship between r, which is the radius of the circular motion, and B, which is the magnitude of magnetic flux density? When a charged particle go into a magnetic field, that charged particle will experience magnetic force. The magnitude of the magnetic force can be calculated by using the equation BQV sine theta. This is the formula that we can use to find the magnitude of magnetic field. Sorry, I mean the magnitude of the magnetic force, not field, yeah. BQV sine theta. FB represents magnetic force, B is the magnetic flux density, Q is the charge, and then V is the speed or velocity, and then theta is angle between B and V. And then, since our charged particle has this force, so our particle will perform uniform circular motion. That means this magnetic force provides the centripetal force. Since it moves in circular motion, we can use equation of centripetal force. F equals to mv square over r. The force that provides centripetal is this magnetic force. That means I can substitute FB into F. Then I will get BQV. I will ignore the sine theta because the charged particle is projected perpendicularly. That means theta is equals to 90 degree. Since theta equals to 90 degree, then sine theta is equals to 1. So we can ignore the sine theta. I got BQV is equals to mv square over r. I can cancel out 1v here. Then I will express r in terms of B. From here I will get BQ is equals to mv over r. That means r is equals to mv over BQ. If I assume mass, velocity, and Q are constant, that means R is equals to K over B. R is equals to K over B is a reciprocal function, and then for reciprocal function the graph is like this. This is graph of reciprocal function. Then my final answer is number 6. R is equals to a constant over B, or we can say that R is inversely proportional to B. This is called as a reciprocal function. The graph of reciprocal function is number 6. Okay, this is the answer for question number 18. Let's move to the last question in this paper. Last question, question number 19. The Quark model states that constituent particles of matter such as proton and neutrons are themselves made up of elementary particles called quarks. So basically, protons and neutrons are made up of another particle which called quarks. For example, a proton is composed of 2 up quarks and 1 down quark. So basically a proton is made up of 2 up quarks and 1 down quarks, while neutron is composed of 1 up quark and 2 down quark. Each type of quark, such as up or down quark here, carries a specific quantity of electric charge, and the charge of proton and neutron is the sum of the charges carried by their constituent quarks. Let us denote as E the elementary charge. What is the charge of a down quark? So the question wants us to find out what is the charge of a down quark. If you have learned about particle physics, of course you already know what is the charge of a down quark. But if you haven't learned about particle physics, there is another way to answer this question. Simply like this. They tells us that a proton consists of 2 up quarks and 1 down quarks. So I can say that 2U plus D, U represents up and then D represents down, is equals to charge of a proton. 2U plus D is equals to charge of a proton. Charge of a proton is equals to E. So 2U plus D is equals to E. And then U plus 2D is equals to up and 2 down quarks is equals to charge of a neutron. Charge of a neutron is 0 since neutron is neutral, is equals to 0. By solving these two equations simultaneously, of course we can find the charge of a down quark. I want to find D, so I need to eliminate U. Keep it the first equation as the original, and then the second equation I will times every terms by 2, then I will get 2U plus 4D is equals to 0, and then subtract it up. 2U minus 2U is equals to 0, D minus 4D, I got negative 3D is equals to E, then D is equals to E over negative 3. This is the charge of a down quarks. My final answer is number 3. This is the last question on this paper. So thank you very much guys for watching this video till the end. And I really hope that you can understand and learn something from my video. Once again, thank you guys and see you on my next video. Bye bye.